The original definition of a parabola, according to the ancient Greeks, goes like this. First, you choose a point in the plane, which is called the focus. That's going to be this point here. And a line that doesn't go through that point, and that line they call the directrix. And the parabola is all of the points in the plane that are equally distant from the directrix and the focus. This shape here it certainly looks like what we're used to of thinking of as a parabola. And you can sort of check by eye that it has the property that the ancient Greeks described. If you take any point on this curve and you measure the distance to the directrix, the way I have this set up, that's always going to be straight down, and you compare that to the distance to the focus, these distances are the same. Even if you choose a point way up here, the distances are different from what they were before, but for this point, these two distances to the directrix and the focus are the same. Even down here at the bottom point, which is called the vertex, the distance between the directrix and the focus is the same. So this is the original definition of a parabola according to the Greeks. Of course, Greeks didn't have the advantage of coordinate geometry, and we do have the advantage of coordinate geometry, so maybe what we should do is come up with an equation that describes this collection of points. In other words, write an equation with the variables x and y that is satisfied only for points on this parabola. Okay, well, as always with these handouts, before you watch me work on these, pause the video and see if you can work on it on your own. If you get stuck, then unpause the video and we'll see what happens. Okay, so here is a coordinate system that I've put on top of the parabola, and I've arranged it in a very particular way. So I've put the origin at the vertex, and the directrix is parallel to the x-axis. That means that the equation of the directrix is y equals minus a. All right, and the focus, because the vertex is at the origin, right? One thing we know about parabolas is for any point on the parabola, and in particular for the vertex, the distance to the directrix and to the focus is the same. So that means if the directrix is a units down from the x-axis, the focus has to be a units up from the x-axis. So the focus is actually this point 0, a, and the directrix is the point at the line y equals minus a. So let's write a formula for the distance from x, y to the directrix. So we have this point that's on the parabola. Let's measure its distance to the directrix. Well, you know, we have a point here on the parabola, x, y, and this point on the directrix, it has the same x coordinate as our point P on the parabola, but its y coordinate is minus a because it's on the directrix. So we could find the distance between these 2 points just using the distance formula in the plane, but because they're aligned vertically, there's actually a shortcut. We can just subtract their y coordinates. So y, for the y coordinate of the upper point P, minus the y coordinate of the point on the directrix, and that's minus a. And so the distance from the point P to the directrix is just y plus a. Okay, pause the video and work on the next problem. Okay, let's look at the next problem. So find a formula for the distance between our point P, which is x, y, and the focus. Now, the focus, if we look back at our diagram here, the focus is not guaranteed to have any nice position relative to our point P. It might be a little higher, it might be a little lower. If P were way up here, the focus would be a little lower. So we can't really assume that the focus has any nice geometric positioning relative to P, but we do know the coordinates of P, and we know the coordinates of the focus. So we can find the distance between P and the focus just by using the distance formula. So the distance to the focus is, that's going to be the square root of the difference in x coordinates, which is x minus 0 squared, plus the difference in y coordinates, which is y minus a squared. Okay, and there's a formula for the distance from the point P to the focus. Pause the video and work on the next problem on your own. All right, let's have a look at number 3. So remember that the definition of a parabola is that the parabola is the collection of all the points where the distance to the directrix is equal to the distance to the focus. So we can describe the parabola just by writing down these two distances and setting them equal to each other. So we can, in other words, we can write an equation that says the distance to the directrix is equal to the distance to the focus. But we've already written down each of these quantities in this situation. The distance to the directrix was y plus a, and the distance to the focus was the square root of x squared plus y minus a squared. All right. So this is the equation for that parabola with directrix parallel to the x-axis and focus at 0, a. Of course, this seems unfortunately complicated. It seems like probably we could simplify this. So pause this video and try simplifying this on your own. Okay, so let's simplify this. I guess the main thing to do is get rid of that square root. So let's square both sides. On the left-hand side, we get y squared plus 2ay plus a. And on the right-hand side, the square just undoes the square root, so we get x squared plus, while we're at it, why don't we multiply out this squaring? That's going to give us y squared minus 2ay plus a squared. And I've missed a squared over here on this a here. That should be a squared. All right, now we're looking for things to simplify. It looks like we can subtract y squared from both sides, so these are gone. We can subtract a squared from both sides, so those are gone. And then we can add 2ay to both sides. And that's going to give us 4ay equals x squared. Okay, well that's surprisingly simple. So this is the equation for a parabola with focus at 0, a and directrix parallel to the x-axis. All right, so go ahead and pause this video and work on the next problem on your own. Okay, let's look at the next one. So this parabola is similar to the last one, except instead of pointing up, it's pointing to the right. But still, the vertex is at the origin, and we have a focus that, instead of being on the y-axis, is on the x-axis. So its coordinates are a, 0, and the directrix, of course, is going to be the line x equals minus a. Okay, so let's find an equation for this parabola. Well, again, we can play the same game. We can write down the distance from our point P to the directrix and set that equal to the distance to the focus. Okay, so the distance from our point P to the directrix, well, this time the points are aligned horizontally, so we can just subtract their x coordinates. So that's going to be x minus the x coordinate at the directrix, which is minus a. And now we can set that equal to the distance from P to the focus, and that's, again, using the distance formula. It's the square root of x minus a squared plus y minus 0 squared. And then we can simplify this. So x plus a equals the square root of, let's multiply everything out inside the square root here, x squared minus 2ax plus a squared plus y squared. Now we can square both sides to get rid of that square root, and we get x squared plus 2ax plus a squared equals x squared minus 2ax plus a squared plus y squared. Okay, now simplifying, these subtract x squared from both sides, these are gone. Subtract a squared from both sides, those are gone. And now we can add 2ax to both sides, and we get 4ax equals y squared. So this is the equation for a parabola that opens to the right if a is positive, and it opens to the left if a is negative. Compare that to the first equation that we got for a parabola, which was 4ay equals x squared. This one opens up if a is positive, and down if a is negative. So you can see this distance a, it actually plays a pretty important role in determining what the equation of the parabola is, and so it has a name. Since it's the distance from the vertex to the focus, it's called the focal distance or focal length of the parabola.